Art, it's great that I can be here and give this first lecture. We also go back probably 40 years through the DOE programs, from excursions on Lake Tahoe's rivers. He's laughing because he knows just what I'm talking about. To all sorts of interesting discussions where we've been hiking and been fighting and then been friends again, and it's all in good spirit, and you've really learned a tremendous amount from you, and inspired. And we did the Garrisher Memorial issue together in JPhys Chem that was really a nice tribute to the father of both of our photoelectrochemical heritages with Garrisher. I gave the Garrisher lecture here in this room about 6 years ago, I think it was. So it's great to be back. I'm sorry that I've got to give 2 talks in the same day. I'm sorry for you. It's much harder. For me, I can talk all day, right? But you have to listen for all day. So it's like being in an airplane versus being the flight attendants. It's easy for them. It's the passengers that have the hard time on the flight. So hang in there with me. I'll give you 2 talks, neither of which have anything at all to do with what most people would associate with our long body of research. I'm just doing totally different things in the last 2 years than what I've done in the previous 42 years. That's perfectly fine. It's interesting. It's hard. It's also keeps things exciting. So if you thought you were going to hear about solar fuels, if you thought you were going to hear about semiconductor electrochemistry, and you're interested in that, you can just leave right now, because you're not going to hear either of those 2 things. There are lessons. I like to talk to the graduate students a lot. The lesson here, the second talk, was an experiment that, quote, didn't work. And without the postdoc, Bryce Settler, who I give a ton of credit for making the observation on the experiment that didn't work, that we had no possible way of expecting to see this effect, there wouldn't even be a talk. So it's not like we planned it. It's not like I had grant proposals written in this area, but it's, in terms of the lab science, the only thing I'm now working on seriously for the last 6 years is based on the experiment that didn't work. So I'll tell you about that in the second talk. But in the first talk, I'm going to tell you about something that I have no business doing at all. And I have no grant money for this, but the stars aligned to let us do it anyway, and it's making a big impact. It's about, now this actually subject that people at NREL are masters of, and so I really respectfully, humbly hope that we'll have some value added in this contribution compared to the professionals that work in this area, of which I'm just an amateur. But I think there are some new things here that I'm pretty confident that policymakers love. They love to hear it. And I think you'll see why. Well, there are now states, 15 states have some type of law carving out electricity systems within your lifetimes, and hopefully mine, that will be completely decarbonized. Some of those laws stipulate that you have to have net zero emissions. Others stipulate that you need to use zero carbon resources. That means you can't even burn natural gas and sequester the emissions. And others are different flavors. Well, almost all of those have carve-outs or goals to have generation be essentially exclusively from variable renewable resources, in other words, wind and solar. And there are a few claims that you can do this. One can make a reliable electricity system based on wind and solar with only natural pumping of water uphill into existing reservoirs. Mark Jacobson at Stanford is a key proponent of this. Most of those claims have been rebutted because they fail numerically, because there simply aren't enough reservoir volumes to do this. And almost all of the water in reservoirs is not used for electricity generation, but is used for agriculture and drinking. And hardly any of it is repumped uphill, even if you could do so. So there are lots of controversy into that. But there are claims. There are claims that this can be done reliably. And they're all, as far as we can tell, anecdotes. You can read in the wind lobby that although the wind is intermittent over even a statewide scale, the wind is always blowing somewhere. There are explicit statements that say this. There are explicit statements that the wind always blows somewhere in Europe. There are explicit statements the wind always blows somewhere in Texas. Then there are equally anecdotal statements, even by the last president of the United States, that say this is ridiculous, that you can't count on intermittent resources, and there's more color in that language. But the point is that it would be helpful if there were actually a data-driven basis for analyzing the variability of the natural resources that nature gives us on our planet. And I would go to many of these technology policy meetings. In fact, I did that for 5 or 6 years, and Doug Arendt was in one of them when we co-chaired a workshop in Aspen. And I would ask people to see data. And I never got any data. And they said, well, you're not in this field. I said, well, I know what to do with a time series of data, but please let me see some data. There weren't any that we could see. And the reasons that were given were wind developers won't give you the data because it's considered proprietary. And besides, they only develop, even though they get a tax credit for every kilowatt hour of wind that's produced, they don't want to tell other developers where they're producing it. And besides, those are only where people have decided to install wind turbines, not where you might want to install wind turbines for the benefit of grid reliability, if you thought that was the first consideration. And the same thing with solar. Actually, there were no data on whether or not there were actually 5-day periods, as I'll show you, when there are solar droughts over the entire state of California, when literally insolation on 5 consecutive days is less than half of what you would have expected historically for those 5-day periods. There was no data. So what did we do? I was on a mini sabbatical, out of my field entirely, just visiting a not very close colleague at the time named Ken Caldera at Carnegie Science. And I was just trying to figure out whether or not there was anything I could learn of ocean acidification and climate science from Ken. And I then one day wandered in at lunch and posed this problem to him. And Ken said, well, I know how to do this because there's a data product from NOAA that will let us actually reconstruct the physical state of the atmosphere every hour. And then we'll put these wind turbines and solar panels anywhere we want, and we'll build a sim city, basically, and understand the variability of the resource around the world hourly, since satellites have been up for the last 39 years. Now it's 42 years. So we did that. Now, how did we do that? When we didn't write a grant, and when nobody seemed like they wanted to know the answer, and when we couldn't have gotten a grant from DOE. Stars aligned because it turns out Ken now actually works for, but is a close advisor to another mutual colleague of ours that Ken and I both happen to know. And so we literally just emailed Bill Gates and said, will you pay for this? And Bill said, no problem. And so from then on, we can do this project. Okay, so I have no business doing this. It's not something my graduate students are trained to do. And it's not something where I could even get a grant for, but it's something you would think someone just has to do if we're going to make good decisions. Now, what are the statutory requirements for an electricity grid in all of North America and Europe? You have to plan your resources according to resource adequacy so that you can meet demand for all but at most 1 hour in a decade. You can't plan and get permit an electricity system unless it meets that criterion. Now, that doesn't mean that you won't have a local blackout more often than that, but that's not the utility's fault. That could be a weather-induced downage of a pole or something else. That's reliability. And technically, we're talking about what's called resource adequacy planning. You have to have enough resources to be able to meet demand for all but at most 1 hour every 10 years. That's 99.998 greater percent reliability, actually, to resource adequacy. Will the infrastructure of an electricity grid last for more than 40 years? That means that you can't plan data based on 1 year, which is what all utilities are limited in capability to do now. They run the so-called Plexos program, and they run 5-minute load balancing for a year. And then they can file with their Public Utilities Commission that they'll have adequate resource capabilities for the next decade based on a statistical analysis of the 1 year. But we took the attitude of once you get fossil out of the system and you don't have so-called firm dispatchable resources anymore, and you're subject to the natural variability of wind and solar, what does nature give us? Well, the answer is that if you take the best case, and this is again something that none of the sophisticated grid modeling programs do because they're interested in 5-minute local load balancing for what's called capacity expansion, where to build the next generation system or wind farm or turbine. And we don't even want to do that. We're interested in the bigger grid scale, longer time steps of every hour over the whole continental United States, over 40 years, of what if you had perfect transmission, single node, you could get electricity from anywhere it's generated to anywhere that's needed. It don't get any better than that. About what the minimum variability would be if you could aggregate everything from resource to any demand, and then let's constrain further from that. What you see is that this light purple line is the variability over 40 years, hourly averaged of the wind. And you see two things. One is that in 1 year on, say, April 1st, it might blow a lot. And the next year on April 1st, might not blow at all. The second thing is in 1 year on April 1st, it might blow a lot. And on this next day in April 2nd, might not blow at all. So the variability in sun averaged over the entire lower 48 is not anything really. It's just seasonal. We'll get to that. But the variability in wind is enormous. It is not true that the wind always blows somewhere on average, even over the entire United States of America. It's worse in California. I'll show you that. It's worse in Europe. We've done this analysis now for 43 regions around the world, quantitatively, of understanding the geophysical-based variability of covariability of both wind and solar, because the argument is always that, well, the sun will shine when the wind doesn't blow. That doesn't happen, especially because there are 3-week periods when the wind goes into the so-called summer doldrums, as all the sailors in the Bermuda Triangle know when the boats don't go anywhere. And I guarantee you that there's a German word for everything. In this case, or the word is called the Dunkelflaute, which I learned means fear of the calm night. That word was invented before people thought about variable renewables, but it's the same fear of windless, calm, sunless nights that are consecutive, that are going to dictate the energy system, because you can't build it on average. You've got to build it based on the extremes. Okay, so that sets the stage. This is what an 80% reliable system would be. People say, well, we can build solar and wind, 80% emissions we could cut right now. We actually could. If you built enough generation to, on average, supply demand in the United States, you could lower emissions based on wind and solar deployment by 80%. This is actually in the Biden plan. It's been on the table for 10 years. And that means that you would miss meeting demand by a hugely unacceptable amount. You would have weeks worth of blackouts every summer across the United States. Now, it's one thing to have a blackout in your county. It's another thing to have 50% less load shedded across the entire nation when you'd have to shut down half of everything for an unpredictable amount of time. People that say you can do this with demand management are failing to quantitatively understand the depths of these demand lulls relative to generation. You just can't possibly meet this with demand management and load shifting. You also can't possibly meet this with so-called vehicle to grid, with carrying around your spare battery storage and electric vehicles and then pumping that back into the grid to meet a demand load like this. Because if you electrified all 150 million light-duty vehicles in the country and you discharge 10% of their batteries all to meet one of these lulls, that would get you through 2 hours. And we have consecutive weeks that we need to deal with here due to this issue. We have what's so-called the LIFO stack, which is the amount of storage you would need as a function of the amount of consecutive hours you would need it for. And once you have that, you can then, without anecdotes, but based on data, say, how many batteries would you need and how would they cost and how much would you deploy if you wanted to do this all load filling, because once you don't have natural gas in the system, you can't load fill based on existing variable fossil fuels. So you've got to store it or you've got to overbuild your generation. You cannot overbuild solar to compensate for a dark night. You can overbuild wind, but you end up overbuilding that generation by almost a factor of 10. I'll show you all of this later on also. So what do? Once we have that data, we then, which is geophysical and is not going to change, we then put it, and it's now 42 consecutive years of hourly weather data at 0.5 degree grid resolution, so about 60 kilometer by 60 kilometer over the lower 48 states. We also have it, as I said, and I've published it for 43 regions around the world, and I'll show you a little bit of that. Then we have to take that data, and other than publishing it so people will understand that you need a lot of storage of these different periods in order to meet reliability, we then can actually put it into a model that deploys assets that we're going to build a sim city of a future electricity system. And we'll build whatever we specify, wind and solar, and we can build concentrated solar in here, and we can put in storage, and we can put in fossil, we put in anything we want. We minimize the cost with an optimizer that does basically what Google Maps does when you tell it, find the shortest distance between point A and point B. We do not pretend that this is a transition path. This is an end state. We also do not make policy, and we do not project future costs and have a recipe for success, because we don't believe anybody can predict future costs. And so what we will do is parameterize around a range of scenarios with no bias, because we're not selling anybody anything, and try to understand not only what the global least cost solution is, but how many close solutions are there, so that if you go down a trajectory that isn't the perfect optimal to get you the hole in one, that you still are on the course and you aren't off in the rough and are going to waste a lot of money rebuilding to get to the end. We get a lot of pushback from the modelers that say, but your numbers are not realistic, building and learning and scale and future projections of cost declining. We don't do any of that, because you can get any outcome you want based on how you project future costs and learning and assumptions. Everything is to understand the fundamental dynamical relationships with EIA published current costs. If you did this tomorrow and waved the magic wand and said, I want to build tomorrow overnight a system that comprises this and that, that's what we give you. If you don't like that and you want transition paths and you want all these other projections, then you don't have to listen to anything we have to say. So now let's break some myths. If you do this, there's a myth that says, in fact, you can read it in many DOE reports, and you can read it in a lot of battery company literatures, that when batteries come down from $200 or $300 a kilowatt hour to $100 a kilowatt hour, that levelized cost of wind and solar electricity will be the same as natural gas right now. They have to come down by a factor of 2. Actually, that's half right. On average, if they come down by a factor of 2, that would be true. But marginal costs on an existing natural gas backed up electricity system are not the same thing as the cost of de novo building a fully reliable electricity system where there is no gas based on these variable resources. In fact, the amount of storage that you need in order to get you through these Texas-size events and the lulls is so large that battery costs have to come down by a factor of more than 100 to where they're far lower than even the raw materials costs in any conceivable on the table battery so far before electricity system costs would be comparable to the ones that we have today. Factor of 100. Why is this? Because you've got to get through those lulls and you need to build more and more energy capacity used less and less frequently. The easiest way to do the quick math is, let's suppose batteries cost $100 a kilowatt hour, which no current battery does. But you meet the DOE goal in 20 years, $100 a kilowatt hour battery. And you use that not once a day, but we're going to use it 10 times a year. If it lasts for 10 years, then that $100 a kilowatt hour battery costs somebody $10 a kilowatt hour every year to own. If you use it 10 times a year, then every time you use it, it costs somebody $1 a kilowatt hour to use that battery, and electricity costs now are 5 cents a kilowatt hour. You don't have to do any sophisticated math to know that you're off by a factor of 20 or more, and it turns out because of depreciation and other stuff, it's more than that. Okay, so this is kind of the basic understanding of why we're not going to get out of reliability constraint by doing it with battery storage alone. Well, then you could say, well, what is there that could scale to that level and be affordable? And if you look at the charts as of 8 years ago when we started, that was pumped hydroelectricity. I've already told you there's not enough water. It's not even viable to do that. There's compressed air. Compressed air storage is limited in siting and actually has other problems. And then there's a whole bunch of batteries, and I'll tell you about redox flow batteries later. But there actually is another scalable technology, and that's in the designation of PGP, power to gas to power. And what that technology is pretty simple. Take otherwise curtailed electricity from wind and solar and electrolyze water and store the hydrogen underground and then burn it in either a fuel cell or a 100% turbine, gas turbine upon demand, power to gas to power. And I'll show you that even at current cost today, that power to gas to power is a cost reducing, credible long-term storage technology to compensate for the variability of wind and solar. And it's the only one we've identified so far. And actually, the person that did this, that really led this, is a graduate student in my group who has a special note here because her name is Jackie Dowling and her aunt is Maggie Tolbert. So we have a good CU connection there already, and everybody who knows Jackie is really proud of what she did. But the basic bottom line is that electrolysis to hydrogen is often poo-pooed because the round trip efficiency is only about 50%. And a battery is 90% in versus out discharge. But the cost of storing a joule of energy in hydrogen is 1,000 times cheaper than the cost of storing a joule of energy in the best battery. And you should use one technology for everything. In fact, you should use batteries for short-term power cycling for a few hours of load. And if you have a cost-favored energy technology, then you slowly charge or discharge that, just like a Prius, buffers from the gasoline engine to the batteries. And so you plug in that technology into the model, and you let two things vary, the power costs and the energy costs. And what you see is this is our scorecard. This is a summary of about 6 different publications, one on each topic that you can read the papers of, but I'm just going to give you the scorecard. These are all at current costs. First is that, of course, right now, in a 100% reliable system, the cheapest way to do that anywhere around the world is just burn natural gas. Yes, people say that wind and solar are the cheapest electricity source if it's on the margin on top of a natural gas backed system. But actually, if you've got all that gas there, it's cheaper just to burn it all right now than it is to put the wind and solar on top of it, unless you value carbon emissions. The next point you see is that, yes, nuclear is more expensive, and we have no bias as to whether or not we should do that, but I'll tell you a little bit more about the pros and cons of nuclear as a fill later on. That the most expensive electricity system that's reliable over this 39-year period you could build would be one which is exactly the policy of the state in which I live, which is to focus on solar with battery storage. It's 3 times more expensive than natural gas today. And the reason for this is pretty simple. One is no amount of batteries can store the variability in the sun between the summer and the winter. So there's a factor of 3 generation there you have to deal with no matter what. Demand does not vary by a factor of 3. And so you've got to make that up with excess generation that's otherwise curtailed, and then buy enough batteries to get you through 3 or 4 consecutive days of solar droughts, not just one. And if you add all that up, you get something that costs you 3 or 4 times as much. The second point is that if you do the optimum wind and solar generation mix, and this is across the continental United States, and I'll show you more about that later, that even then, even at current costs, and electrolyzers and fuel cells are not mature at scale, so there's plenty of room to go down, that if you add them in, that you lower costs. And it is a credible, cost-effective, relative to just batteries, long-term grid storage technology. One more point. People often say, well, what if we just tolerate not meeting demand for more than 1 hour in a decade? Let me give you 5 hours in a decade. We actually accommodate that by putting in a cost of so-called lost load. And the economists will tell you that's about $10 a kilowatt hour, which is basically the prorated value of running the economy of the United States. And if you shut down all the electricity, you basically shut down the economy, and that's the damage loss. So we put that in and say, if you're willing to suffer a $10 a kilowatt hour penalty and shut load down more often, how much would that save you compared to forcing you to build it to meet all load? And the answer is hardly at all. And then we can lower the cost of lost load, and it still doesn't change anything. The other point is that not only do even at current costs, power to gas to power reduces system costs in all cases, but In addition, when you look at the electricity costs on this so-called contour plot as a function of a reduction from current costs of power to gas to power versus reductions in the cost of batteries, that you cross many more contour lines going that way than you do go that way, which is exactly the opposite of, to my knowledge, all state and national public policies that all are focusing on lowering the cost of battery storage as opposed to lowering the cost of a credible long-term storage. When you do much more for electricity system costs to lower the cost of long-term storage than you do short-term storage, no matter what costs you put in that future projection. So why is that? The reason for that is that the optimal wind solar mix and anything approaching that within this constraint, by the way, of perfect lossless transmission across the United States only has 1.7 hours of average load in batteries and almost a month, half a month, 16 days worth of storage in the long-term store. This actually doesn't change regardless of the costs of short and long-term store that you put into the model. For all of you physical scientists in the room, I can't explain it this way to policymakers, but I can to people here. If you do the Fourier transform of the variability, there are only two peaks. There's one peak that's the seasonal storage, and the other peak that's the wind variability and hourly storage. And so you've got to back transform it to minimize that difference between demand and supply. And so there are only two technologies that you need to fit those two peaks. One is 2 hours worth and the other is 2 weeks worth. So you shouldn't build something, as I'll tell you, that's 10 hours with low batteries because there's no peak there. And so there's no grid services role for that. It's pretty interesting. In addition, you see now, and we'll tell you more, the difference between the objection you get from using one technology entirely. The objection would be if you just use hydrogen as power to gas to power, you only have 50% round trip efficiency, versus the objection for batteries is you can't do long-term store of these are cheap for power cycling. You use them for where they're cost effective. This is cheap, really cheap for energy storage, 1,000 times cheaper. You use it to cycle once or twice a year. And furthermore, we actually show that the so-called dispatch curves show, interestingly, that you actually exchange energy between the short-term and the long-term stores by itself, even at periods of constant demand. There's another subtlety here that isn't so subtle in the big picture, that is an area still for research. In all of our analysis, we've taken the 39, now 42-year weather record and assumed so-called perfect foresight. That is, you knew on year one what would happen in all the next 39 consecutive years. And that's great for a scientific analysis, but it's not the real world because you're not going to have perfect foresight in the next 40 years. And so part of the next research project is, what does a rule-based system where if costs go above a certain value, or if you build more storage, how much is enough to get you through? And how would you behave if you're a rational economic operator? How do costs have to be set so that you don't pay too much for your storage when you don't absolutely know how much you're going to need, but you can get through the once in every 10-year wind drought, for instance? And we do this based on real data that I've shown you that is sorely lacking in almost all other economic analyses. Mostly what people do is they'll take one bad day in a year and then project that for the next 10 years as opposed to the average. Or they'll take a few average weeks, or they'll do some other synthetic data thing, because there hasn't been this emphasis on taking weather data and using it to derive the physical state of the atmosphere as opposed to using existing asset generation historical data. Another point is that if you have long-term storage, you don't just use it for 1 year. In fact, I can explain this to this audience. The RC time constant of the natural system is several years. That makes sense because we all know water has an interannual variability when there are years when you get more and years when you get less. But that also happens with the wind. There are years when you get more and years when you get less. And if you have the long-term store, you use it to buffer the interannual variability that the natural system has, that otherwise the only way to get through is to overbuild your generation enough to get you through the once in 10-year wind drought year that you don't necessarily even have data to project in the future for. So you have to overbuild that in order to meet that. But if you have a long-term store like hydrogen, you don't have to do that. No utility has the ability now to plan for multiple years in the future because they all run Plexos for 1 year worth of data. And this is another interesting geophysical contribution. Well, then we can say, what happens if you were a utility and did that? What happens if you actually took a year's worth of hourly wind and solar data and built a system and went to the Public Utility Commission and said, good, I want to build that and I want to run it for the next 40 years. How reliable will that be? What you can see is that when you do that, no matter what year in the 39-year record you optimized over and met load in that year, that system never meets regulatory load filling in any of the other 39 years. Which tells you, obviously, that you can't build a system based on 1 year of data and expect to get it through 20 years of operation, because it's just not going to work that way because nature doesn't cooperate. This is another interesting question of what do you do? And actually, we have a paper where we're just ready to publish this, literally titled, "How many years are enough?" Right? Because we have to think differently if we're not going to base resource adequacy planning based on the ability to have firm dispatchable fossil electricity. And no public utility has a policy in place on how they will set reliability in the face of unknown variability of their resource. This will help them do that. You can talk about hydrogen has a bad name because of the visions of transportation and storage and above ground tanks. There's actually plenty of room. You'd store it not even in salt caverns, but almost all of it could be stored in the natural geologic reservoirs, of which there is already 4 trillion cubic feet of natural gas for seasonal storage in these underground reservoirs. Now, again, this is a one-size-fits-all. If you look at power to gas to power techno-economic analyses, they almost all say, well, we're going to put them in salt caverns and have to mine out the more custom salt caverns because there's not enough capacity in that to handle all the variability. And you need to have a salt cavern because we need to be able to get that hydrogen all in every day and get it all out every night to compensate for the solar variability. But that's not what the real data say. What the real data say is you only need to charge and discharge that on average once a year. And so what you really should do is you use the big balloons, the salt caverns, to give you the pulses that you need. And then you have your energy piggy bank and all of where we have natural gas now. And if you're not going to use the natural gas anyway in the future, you might as well repurpose those existing reservoirs and put hydrogen in. And you only need 60% of the existing cavern space already in place, already with transmission for gas, already there in compression, in order to store all the hydrogen you need in order to satisfy the power to gas to power requirements for CONUS under these conditions. The situation isn't perfect worldwide, but we've done the analysis there also. You can read about that in Nature Communications, where we actually have the same geophysical variability for regions like Europe, for countries And for regions like Hawaii that are going to have to face the fact that they have 100% renewable law, it sounds great if you're an island of, we'll have 100% renewable electricity within 20 years. But pulling it off is another story reliably, because when you look at it, it ain't so easy. Most of their people are on a small island. Most of their electricity generation would be on the big island. There's a big, deep undersea cavern on that volcano with sensitive tropical reefs offshore that's going to make it a neat trick to get all that electricity from one place to the other. And then how are they going to store it all anyway? And I guarantee you, I know Carl knows, and I know I've been in Kona events there when the sun doesn't shine over the whole state for 5 or 6 days in a row, and it's miserable. Okay. And no amount of batteries is going to get you through that. California has a similar law. We did the analysis in support of California's so-called SB 100 bill and presented it to the Energy Commission and their Public Utilities Commission because nobody else had done this. Although we made a law in support of reliability, nobody had actually done the data analysis, but we could do it, so we did. And WEC is the Western Interconnect. It would involve not only California as an island, but also expanding transmission so that it could accept and parasitically take all of the wind that it needed from Wyoming and Colorado and Montana in the Western Interconnect and use it for the greedy Californians' energy purposes. There's a law saying we're allowed to do that, but it's not clear you would be able to do that. Nevertheless, even if you did, this was the variability in the United States. This is the variability of the wind in California. Of course, it gets worse. It gets more variable. You even need more storage if you constrain it to a region that's smaller than the ideal load balancing of the lower 48 states. What's more interesting than that, at least to me, is that these are the so-called wind and solar droughts. It's no surprise that if you're in a state as opposed to a country, that I told you there were wind droughts across the country, so there are certainly wind droughts across just California. That's pretty easy to understand. But there are also, over a 10-year period, as I said beginning, 5 or more consecutive days when there is at least one episode in a 10-year period when there's less than 50% of the insolation than you historically expect over the entire state of California. So furthermore, if you're like me and you live there in September of 2020, when we had all those wildfires, that if you drove across the state, the sun was orange for an entire month. And those solar panel productions went down by a factor of 2 for the entire state for an entire month because of wildfires, presumably climate change induced wildfires that are reasons we're going to renewable generation that are inhibiting the renewable generation the more we get the wildfires. So we need even more storage than that to get through that period of time. Furthermore, if you have that long duration storage, you don't have to depend so much on that optimal wind solar mix, which California doesn't have, because in fact, the total wind resource of California is that asterisk star right there. And you can see that if you pin the wind capacity there and you have to go away from the optimal wind and solar mix in order to minimize the variability, the covariability over these 40 years, there's even more of a case of the cost benefits of adding long-term storage, because you've got to have some way to do this. Otherwise, you've got to really overbuild your wind to get through those dark nights, and you just don't have the resource to do that, even if you go offshore. There's another option. If you can't do this with demand management, you can't do it with storage, then the other way to do this is to do flexible demand, which would be, as an example, so-called electrofuels, where we'll take excess electricity in the summer and we'll put it into something that could be a flexible load, not an hour or two load shifting like residential, but An example of that would be electrolytic hydrogen, and whether you use the hydrogen for transportation or storage, or whether or not you convert it with CO2 to a liquid fuel, you're able to time shift when you use that load almost arbitrarily, right? You put that oil into a tank and use it 3 years later. Why do we care? So that's a generic flexible load. And then we ask the question of how much free electricity would there be for flexible loads where you could take that otherwise curtailed electricity and convert it into stored liquid fuels or gaseous hydrogen without impacting your need to build more capacity. Because it's not free if you have to add more generation capacity just for that purpose. But if it was already there because you had to overbuild generation to compromise on your need for storage, then if you can divert it into this other channel, it's paid for by the electricity system assets. The electricity so-called operating costs are low, was already there, and you pay for the conversion costs. That study showed an interesting thing. It showed that actually, if you were to parasitically take up to 20% of the energy that would be available and convert it into a flexible load, that you could run that generation, even if it were up at wind solar, at a capacity factor of better than 90% of the time. Doug even is thinking about how can this be? If you're running it off of wind and solar, why isn't the capacity factor of this excess generation pinned by a 20% capacity factor on solar or a 40% capacity factor on wind? Is because it's grid connected in this model, and because the system is designed to meet peak load. And so at all other times, other than those few peak load hours, you've got excess capacity. And it turns out that's 90% of the time for up to 20% of the total load, which means that you can, up to this point, have your cake and eat it too. You can have otherwise very low cost electricity, which has the corollary that if you actually cost this out, if you build electrolysis today at current costs, and you did it off of this 20% of the load generation in a 100% wind solar system, that electricity cost and that capital cost would already meet the DOE goal of hydrogen at less than $2 a kilogram. It only meets it for up to 20% of the wind and solar load, because that's the geophysical variability you're trying to deal with anyway. And it meets it less if you use that hydrogen for storage, because you're competing for that same extra. There are a few more lessons and then I'll stop on this. One is we looked at concentrated solar power. And again, with no bias, CSP is often touted as a very viable contributor to a reliable electricity system because it runs 24/7 in principle, because you concentrate the solar heat and either put it to a PV system or directly heat a molten salt. And actually the molten salt storage can last with good thermal insulation for even up to a month. And the levelized costs are something like 15 cents a kilowatt hour. The proponents of this say, well, by the time you put batteries in with PV and batteries, it's higher than that, at least right now. And so you've got one camp trying to advocate for the role for CSP, and another camp saying, but PV costs are still coming down, and so are batteries. And so that will change very soon. It doesn't have to change by very soon, because again, this theme of marginal costs are different than actual system costs. If you have to have reliability, when we put in essentially any reasonable cost, both current and reduction in CSP compared to current, we find almost no cost reduction due to deployment of CSP in a totally reliable decarbonized system. The reason for that is that the generation is actually very expensive. It's when you think about the solar mirrors and the generation part of CSP, it's 3 times more to generate a kilowatt hour than PV is. But the thermal store is actually less expensive than batteries. And so actually the role of CSP plus thermal storage is limited to a very little niche when you're trying to just use the thermal store, which you might as well have done with the resistive load, heating up that thermal store. It didn't need to come from the high temperature heat. You could have just melted the molten salt anyway and used it as a cheap store to augment your peak load shaving. People don't love all this because, you know, there are companies going out and hawking, including those of redox flow batteries. This is the biggest redox flow battery in the world. They're the size of Walmart's, right? And because the energy density is something like 20 kilowatt hours per liter, and a lithium battery might be 10 times, 20 times more than that. But more importantly is, I've already told you the answer on a geophysical basis to whether or not there is a role for a midterm storage technology. Now, California, my state, has a regulation that says we need to develop 10-hour stores because that's considered long-term. But I already told you there are only 2 peaks in the Fourier transform spectrum, one for the short-term hourly storage of the wind and the other for the long-term seasonal storage. And our modeling shows that exactly on costs. It is no matter what redox flow battery you put in, no matter what cost for a 10-hour store, there's only 2 limiting cases. One is their power costs are so cheap that they're the short-term store and you only build 2 hours of them and you displace lithium batteries, or their energy costs go down by a factor of 100 and they're so cheap they displace hydrogen as a long-term store, and then you build 17 days of it. And there's no scenario when, if you have a short-term and a long-term store, when you would actually ever even deploy a midterm store for 10 hours, because physically there are only 2 variables that are of concern: power and energy. And if you've got cheap power in short-term batteries and you've got cheap energy in long-term store, if you've got a midterm store that's inferior for both power and energy, you're never going to deploy it. And it's never going to lower anybody's costs, because you need to have both the short and long-term store. And once you do, then you can swap power between them like the Prius. And there's no role for a 10-hour store and a reliable grid, unless you want to pay more money for it than if you did it the other way. Oh, the battery people don't love us now either, but we're not selling anything. All right, so what are the conclusions of this so far? This data-driven analysis shows unarguably the inherent variability and availability of wind and solar resources. So at least we can put to bed the non-data driven anecdotes of whether or not you can build a reliable system just based on wind and solar. What happened to the nuclear? Did I skip that slide? Huh. Okay, well, I guess I'm going to go back, which I shouldn't really do, because in the conclusion, and I didn't talk about it for some reason. So if you don't want to do batteries, I'll finish this because it's in my train of thought right now. Sorry about throwing it off. Then there is a whole advocacy group saying, well, this is the perfect role for nuclear power. Because if we can build flexible, load following, small modular nuclear reactors, that they will be wind and solar's best friends, and they'll take the role of natural gas. And they'll be the fill that will obviate our need for battery storage. So we can analyze that. And we can say, if you take nuclear power with no bias and lower its costs from the present in the optimal, reliable wind, solar, battery storage, and nuclear mix, does nuclear power complement wind and solar, or does it just compete with it? And the answer is always it just competes with it, no matter what the costs. If I explain to you why in one sentence, you'll all get it. Wind, solar, and nuclear all are characterized by high capital costs and basically free, no variable operating costs. If nuclear power is cheap enough to be able to fill for wind and solar and be used only a fraction of the time, then it's even cheaper to use it all the time and not have to spend money building that wind and solar in the first place, because all that does is raise your costs. The other way to think about it is because the variability is so large of wind and solar, you need to build so much backup to fill that you might as well use the backup all the time. And it's cheaper to do that than it is to run the wind and the solar at all. So it's never the case. And furthermore, what if you did build a flexible variable nuclear plant? It's still cheaper to run that all the time than it is to use it only for variability to fill for the wind and solar, no matter what the costs of the wind and solar turn out to be. So we didn't make friends with the nuclear community either. We didn't make friends with the flow battery people. But that's okay. That was the point of that. There's hardly any value in flexible nuclear. The nuclear competes with wind and solar. It's not its friend. It's just a pick'em. Yes, it's true that there's public perception issues. I am not personally for or against any one of these decarbonization. I'm not selling you anything. I'm just telling you what the data say about what the value in a reliable, decarbonized, full electricity grid would be. There's one more caveat here, which is that if you didn't build according to the letter of the law, if you were willing to let natural gas with carbon capture and storage be a fill for wind and solar at 80% carbon capture, given you're only using it for 20% of the energy, you would cut emissions by 96%. That's the math. You would have 80% reduction off the 20%. You'd leave 4% of the emissions. But the law says you have to get to zero. And all of these costs and all of this extra layer of structure are the difference between the 4% emission residual and the zero. And so how idealistic and pure do you have to be if you're worried about a cost-effective way of reducing, but not necessarily getting to zero or net zero on the emissions? We don't project future costs, but it's something to definitely keep in mind that all of this analysis was based on the predication that we were constrained to have no emissions at all, right? And there is a value judgment that's going to come into play when someday, sometime, someone is going to figure out that it's going to cost a lot more to get that last 4% than it is to get the first 96%. And do we want to go down that path or not? At current costs, power to gas to power just reduces costs, and it's only going to get better. It's only going to get cheaper as we deploy more power to gas to power. And well, actually, they did a study for the LADWP LA100, and although it had less data in it for the variability, they concluded the same thing. And they do have a role for both ammonia and for hydrogen in their scenario for decarbonization deeply of Los Angeles DWP. So this is not the only work that resonates with the need. In fact, our local utility, SoCalGas, basically says it pretty simply. They think we are roughly going to need equal contributions of clean molecules and clean electrons. And that's probably about right. And so when people were to say that we will do everything with known technology and we're going to decarbonize our electricity system just based on wind, solar, and storage, well, we could do that, but it would probably cost a lot of money to meet that last little bit of emissions. And you don't fulfill all the energy services that we currently need to fulfill. There's probably a middle ground there. Flexible loads counterintuitively can operate at a really high capacity factor using low cost electricity for up to 20 or 25% of the average energy produced by that grid. There's not really much of a role for CSP and thermal storage in almost any cost scenario. We know Chuck may not like that, but it's what our data tell us. And the short and long duration storage are essential for reliability. I also told you that you would do more to lower electricity system costs by doing R&D into lowering the cost of long-term storage than you would by lowering the cost of short-term storage. But I don't know of a single utility that is doing that, as opposed to placing a lot of emphasis on deploying and cost reduction in battery storage and not in where the long pole in the tent is, which is in long-term storage. And so that's a message that we give to policymakers whenever they are willing to listen to us, to try to make sure that they're balancing the long poles in the tent here. And we don't just focus on the short-term store or a 10-hour store. And then if we don't have a long-term store, we just are out in the dark, literally. So those are those conclusions. There's one more point, which is pretty interesting too. When we did this for California, California, of course, is hydro heavy. We have almost 50% of state electricity generation from other people's hydroelectricity. And the PUC said, well, we're not going to shut that down. So we've got that. So let's build not 100% wind and solar. Why don't you remodel 50% wind and solar, and we'll take the other 50% for hydro, and surely it's going to be better. And in fact, quantitatively, it turned out worse. Why is that? Because hydroelectricity has its own seasonality. You know, when the snow melts and when the rivers run and when they empty reservoirs is not correlated with electricity demand at all. And so in fact, even if you put in half of your load as existing hydro, the absolute requirement in joules of storage was higher than if you had 100% wind and solar and didn't use the hydro at all. On top of that, we all know that there's obviously interannual variability in the hydro of all the totally dry reservoirs in the state of California right now. So if you actually put that variability in, you would just eliminate your ability to rely on firm hydro entirely, because you'd have to back it up for interannual droughts in such a way that you might as well have not counted on it for generation at all. They didn't expect to get that as the answer, but that's what we gave them, because data are data. We've got a lot of work left to do. Some of the important things left to do, I've alluded to. This is not a real world system, right? We're the first to admit that. It's an idealized system where there's no transmission congestion, when transmission is free and we can put it anywhere in the country from anywhere to anywhere. That's not the real world. That's only going to make things worse, not better, because the variability locally is going to go up as you put impediments into where you can push and pull electricity from. So it's not a real world solution there. It's not a transition path. We don't yet know either how much more money it would pay to be close, but not at the global minimum. How soft is the surface, just like protein folding? And we want to establish that, because in the face of uncertainty of future costs, we don't pretend to have the crystal ball that says that this is what we should do with our electricity system for the planet. And if you follow this prescription, the Pied Piper will lead you to success. We don't dare do that. And so we are exploring what the surface looks like, so that really the opportunity should be, let's keep our optionality open, but build assets that are no regrets, that allow you many paths to, if they're not the cheapest possible path, they at least are a viable, credible, cheap path to get you to the goal, knowing that costs are going to change in the future, knowing that we're not going to be perfect, and we don't have a perfect ability to predict. We're also looking at what I alluded to. This is given a static climate. How will climate change affect where the wind resources are and how we deploy things, and how agile do we have to be? And that's an important question also. And then there was the rule-based question, which is really the boots on the ground one of, we won't have perfect foresight. And so what rule-based system, how much buffer do you need to add to a system in order to avoid the once in 30 or once in 50-year drought that you know is coming, that you have to build assets in order to bridge you through, or you're building a system that you're admitting is going to shut down the country for weeks at a time, and no one wants to build that. And so we have to provide guidance to policymakers, all of which who are struggling with, how do we deal with this new world? How do we carve out regulations based on data that these are data that will allow them to do that, and that we're not selling anybody anything. So we're considered, as far as they are concerned, a pretty neutral gold standard as to help shape how we might navigate the troubled waters. So that's why I'm doing this. I have no business doing this. I'm not an expert in it, but I do have graduate students who are doing this in part full-time now as part of their thesis work. They are collaborating with the Carnegie Science people all of the time. I am totally in this with 2 feet. I go to joint group meetings. We have joint retreats. We publish joint papers. To be just a little on the political edge, we also have a paper that we're submitting right now, which is pretty interesting, just go a little bit. Its title is Renewable Energy is Republican Energy. We make the observation that although not a single Republican senator or congressperson voted for the bill that provided for a lot of renewable energy, that our analysis shows that 82% of the wind resource and 75% of the solar resource in the United States is in Republican districts. Right? States as well as districts. And so it's interesting that states that vote red and districts that vote red have all of the wind and solar resource, because it's pretty obvious if you look at a map that that's most of the land, although it's not most of the people. So that's a pretty interesting observation, just phenomenologically, that how do people vote and provide jobs and economic benefits based on renewable energy for their constituents. So we're publishing that also. And we can do that because I'm not at a government lab and I don't have to worry about things like that. So with that, I hope it was interesting. I'm learning a lot on this project. It's just something I feel we should do.